Oops, there. All right, that's good. Hello, can people hear me out there?
Yes.
Yes, we can hear you.
Oh, good. We have it's the first night class that I've ever given in my entire lifetime. So it'll be a new experience for me. Okay. There we go. We'll just wait a few more minutes so other people can join us. Okay. Again, I just want to do a sound check. Can everyone hear me out there?
Yes, we can hear you.
Okay, great. Yes, so welcome to Math 3300, the night version of the class. This, again, I've mentioned this is my first night class that I've ever taught in my 30 years of teaching. So we'll see how it goes. I apologize for people who are watching Monday Night Football that, we're actually interrupting your football, but hopefully we'll be done by the time the game is over. Okay, so let me start by reviewing a few things. Oh, before I forget, um, tomorrow I'm going to check on the room and I'm going to try to get into the screen share using a different method. So hopefully I'll be successful. But what I'll do is I will keep you up to date in terms of how we're going to be doing class on Wednesday, whether it'll be a hybrid or actually just online. If I can't get it to work, it'll be just online for Wednesday until we get the problem fixed. But hopefully by the end of the week, we'll have the problem dealt with. So yeah, just thanks for your patience. Okay. All right. So let's kind of back up and sort of recall where we're at. So we were looking at bases. So if I have W a subspace of Rn, and we know that W is going to have a basis. So let's say that V1 up to Vt is a basis for W, okay? And so what does that mean? Well, it means first that if I take the vectors, these are linearly independent. Okay. And what other property do you actually need for a basis? Anyone? So what other property do you need for a basis?
What's
Probably
the
not span
dimension?
the vectors.
Okay, so W, good, is a span of V1, V2, up to Vt. Okay, so they're linearly independent and they also span. Okay. Now, now let me give you an example. So let's say I have W to be equal to Rn. Okay. And we know what a basis for Rn is. So a basis for Rn looks like the following. So a basis for Rn is, let's say, E1, E2, up to E sub n. Okay, so where EIs are the unit vectors. So it's 0 everywhere except in the jth spot. Okay. All right. So if I take a vector v, then I could actually write it in terms of the basis. So if v is equal to C1, C2 up to Cn, then this is C1, E1 plus C2, E2 plus Cn, En. Okay? So these are the coordinates of the vectors. And this part over here is V written uniquely as a linear combination of the basis E1 up to En. Okay? So what I'd like to do is I'd like to sort of extrapolate this example, sort of generalize this example. And so if I take a basis for Rn, or just a basis for any subspace of Rn, then what I could do is I could write it in terms of its coordinates. All right. So let beta equal V1 up to Vt be a basis for W. Okay? And so now what I want to do is I want to write a vector in W as a linear combination of the V's. So now let V be in W, and V is equal to C1 V1 plus C2 V2 plus CT VT. Okay, so this is a unique linear combination of basis elements. So whenever you have a basis, you can write your vector uniquely as a linear combination of the basis elements. Okay, so that kind of follows from using linear independence. All right, so now what we can do is we can make the following definition. So we can define a coordinate version of the vector V, and we can sort of write this in terms of the coordinates C1, C2, up to CT. Okay, so these are the coordinates of the vector V with respect to the basis beta. Okay, so if we take a vector, we can write it as a linear combination of the basis elements, and then we just pull out the coefficients. That's all we're doing. And those are called the coordinates. All right, any questions on this? No? Okay, so let's do an example with numbers. Okay, so let script beta, and I'll give you two vectors. Let's see, -3, 1, 4, and 7, 5, 6. Okay, and our V here is going to be equal to 8, 1 plus 3, I think. 8, 1, and a 3. Okay, let me just make sure the signs are correct. Let's see, 8, 1. I guess I get, let's see. I have -3. Okay, so maybe it's a -3 over here. Okay. All right. So what we want is we want to, first of all, determine whether V is in the span of B, and then write the coordinates. Okay? So let's do that. So 1 is V in the span of the set B, and 2 If so, write V in terms of its coordinates. Okay? All right. Now, how do we answer the first question, whether V is in the span of these two vectors?
Right. The two vectors is a linear combination of V.
Good. So we have that we're wondering whether 8, 1 minus 3 is a linear combination of minus 3, 1, 4, and 7, 5, 6. Okay. All right. So, actually, this is weird. Maybe it's a plus 3. Let me check that out. I think it's a plus 3 here. Okay. It will matter. Okay. All right. So let's see if this is true. Okay. All right. So in order to do this, we use Gaussian elimination. So we need to solve a system of equations, right? So we have minus 3, 7, 1, 5, 4, 6, and 8, 1, 3. Okay? All right. So let's see what we get here. Okay, so first of all, let's multiply this first thing by 3 here, and then add row 2 and row 1 together, and then put the result in 3 times row 2 plus row 1 and put it in row 2. So you have minus 3, 7, 8. And then what do we get? We get 0. And then what do we get? 15. I get 22. Right? And I get an 11 here. Okay? And then what we want to do is we want to eliminate the 4 here. Okay? So I guess we'll use the top one again. So when we multiply the first one by 4 and the second one by 3, and then we'll multiply 4 times the first row and then 3 times the third row, and then add it, put in the third row. So we get 0 here, and we get 28 plus 18, that's 46. And then I get 32 plus 9. What's that equal to?
41.
41, right? Yeah, so maybe I want to do something slightly different here. Let's see, 32 minus 9 is what? 23, right? So maybe I want to put a minus 3 here. Sorry about that. Okay, let's try it again. Okay, 32 minus 9 is what?
23.
23. All right, good. All right, so now I think it's going to work. So this is a minus over here. Okay. All right, so notice that each of these is twice the other one in the last 2 rows. So I can replace this by multiplying or dividing by 2, right? Or yeah, dividing by the 11 for the first one. So this is 0, 2, 1. Right, just divide by 11, and then I divide by 23. Okay? So I divided by 11 in the second row and then 23 by the first row, right? Doesn't change the system of equations. And then finally, I get minus 3, 7, 8. And then what do I get? I get 0, 2, 1, and then I get 0, 0, 0. Okay? So what can I say about the system of equations?
It's consistent.
Good. So this system is consistent. And so now we can actually solve to find the coordinates, right? Okay, so what do we get? Well, we get 2C2 is equal to 1. So C2 is equal to 1/2. Okay. And minus 3C1 plus 7C2 is equal to 8. So minus 3C1 plus 7/2 is equal to 8, which is, I guess, 16/2. So minus 3C1 is equal to 9/2. Okay. So C1 is equal to minus 3/2. All right. Okay, any questions on this so far? Okay, so then if I take my vector v here, and if I rate it in terms of its coordinate, so what should I do?
-3/2, 1/2.
Good. All right, does everyone see how we did that? Okay, so to write the coordinates, you just solve the system of equations, right? You write it as a linear combination that turns out to be a system of equations type of problem. Once you you know how to do this by using Gaussian elimination. So you do Gaussian elimination, and then if it's actually in the span of those two vectors, we can actually back substitute to find out what you have there. Once we find the solutions, then we can just write the coordinates out. Okay? Questions?
Could you scroll up just a little bit? I
Sure.
missed some of the words before we started the problem.
Oh, okay. Let me see. Scroll up.
Like a
Farther?
little bit more.
Right here.
Yes, thank you.
Okay, I'll just leave it here just for a second. I will post the notes, of course, online.
So if we did not have a row that was all 0, then this system will be inconsistent.
Right. And you can't write it as, you can't write that V as a linear combination of the basis elements of W. So it's not in the span of V or script V. So then you can't write the coordinates out.
Right, so you basically can almost tell what you're trying to expect just from the dimensions of the matrix, what is consistent and what is not, so to speak.
So to speak, I mean, the likelihood is not that great that it's going to be consistent. So the problem better be rigged in some sense.
Right, of course.
That's why I was struggling with the plus or minus 3. Let me see, let me make sure, since we're on this anyway, let's see, what do we do? It's a minus 3 here. So let me go to this, stick in the eraser, and oops. Okay, so now we'll go back up and we'll do that. And I think it was a minus 3 here. So let's make it a little bit more clear. Okay, everything good?
Yes.
Okay, great. All right, so now we're going to switch topics. So we get to talk about determinants next. So the next topic is determinants. All right. Now, we actually computed the determinant in the 2x2 case. So let me recall the 2x2 case for you. And so we actually found a formula for the inverse. So A, B, C, D inverse, and that's equal to 1 over AD minus BC. And we had DA. So remember, we flipped the D and the A, and then we negate the other two things. So minus B minus C. Okay. All right, so that's the 2x2 situation. And so, so in the 2 by 2 situation, matrix is invertible. If and only if AD minus BC is not equal to 0. Okay, so there's a quantity for which if it's equal to 0, the matrix is not invertible. And if it's not equal to 0, then the matrix is invertible. And in this case, we're going to call this the determinant. So the determinant of the 2 by 2 matrix here is equal to AD minus BC. Okay. Now, what we'd like to do is we would like to find a number for an m by n matrix, such that if that number is not 0, then the matrix is invertible. So we want to generalize this. The determinant for arbitrary n by n matrices. Okay. All right. Now, in order to do this, I have to introduce some notation first. So let me do that. So let A be an n by n matrix. Okay. Now, what does A look like? Well, A is a square matrix. And so let me just start, writing out some of the coordinates. So A11, A12, A1n, A21 up to A2n, N1, ANN. Okay. Now, if I pick a number or pick an entry out of the matrix, then what I can do is I can sort of take out, let's say, the ith row and the jth column. So let's say I have a let's say I have an entry aij here. Okay. So then I want to get a matrix by taking out the ith row and the jth column. So the way to think about that is I sort of delete the ith row like this of the matrix, and then I delete the jth column. Okay, so I just kind of cancel all those entries, pretend they're not even there. And then what I do is I kind of gather the matrix back together again. And so I have a n minus 1 by n minus 1 matrix. Okay, so let Aij, okay, be the n minus 1 by n minus 1 matrix defined by deleting the ith row and jth column. Okay, so let's do some examples where we compute these matrices. So I'm going to give you a 3 by 3 matrix. Let's see 3, 4, and 5, and 1, 2, and 3, and let's say 6, 7, and 8. Okay, so this is a 3 by 3 matrix, and let's actually compute these smaller matrices, right? So let's compute A11. Okay, so how big should A11 be?
2 by 2.
By 2. Okay. And again, what we take this entry up here, this is the 1, 1 entry. And then what we're going to do is we're going to delete the first row and the first column. So we just do something like that, right? And then, so then the matrix is going to look like what?
2, 7, 3, 8.
Okay, so 2, 3, 7, and 8, right?
Yes.
Okay, everybody good with that? Let's try another one. A31. Okay, so the 3, 1 entry is the 8, right? So when I delete the third row and the first column, okay, actually, sorry. What is the 3, 1 entry? It's a 6, right? Yeah.
Yeah.
Yeah, okay, it's a 6. And so I want to delete the third row and the first column. So what's the matrix look like?
4, 2, 5, 3.
Okay, so I'll read it across 4, 5, 2, 3. Okay, and let's do one more. So A22. Okay, so let me use a different color this time, all right? So here's a 2, 2 entry over here. And so we're going to delete the second row and the second column. And then what matrix are we going to get?
3, 5, 6, 8.
Good. All right. Does everyone see how to do that? Nice little rule. Okay. All right. So now with this definition, I can actually define the determinant for you. So let me make a definition. Okay. So again, A is an m by n matrix. And so I'm going to define the determinant as follows. I'm going to take A11 times the determinant of the smaller matrix A11 minus A12 times the determinant of A12 plus A13 and the determinant of A13. So what I'm doing is I'm going along the top row and then I'm taking the determinant of all these smaller matrices. Okay, so A1n, determinant of A1n. Okay, so I'm taking the entries sort of at the top over here. And then I'm taking the submatrices, the determinant of the submatrices corresponding to taking out each of those entries. Okay, so let me give you an example. So compute the determinant of the following. Okay, so we'll do a 3 by 3 since we already know how to do a 2 by 2, turns out. Okay. All right, so let's compute this one out. Okay. All right, so so sometimes what we do to define a determinant is we use absolute values. The absolute value to sort of signify that we're taking the determinant. Okay, so we don't have to write determinant all the time. All right, so again, in this case, we're going to expand along the first row up here and then take the submatrices corresponding to entries in the first row. Okay, so the first one is a 4. And the submatrix we take after deleting the first row and the first column is 5, 2, 7, 3. Okay? All right, then we take the next one is the 3, but we have to take a minus sign. Okay, so notice in the definition, we have a minus sign. So we have minus 3. Okay, so again, we're now going to take out the submatrix obtained by taking out the first row and the second column. So what submatrix do we get there?
6293.
Okay, good. Okay. And the last one is 0. And then we just get 6597. Okay, any questions on this so far? Okay, so we're good. Now we have to we know how to take 2 by 2 determinants, right? So what do we get? We get 15 minus 14 minus 3 times 18 minus 18, right? So the answer is, and then we get 0, right? And so the answer is 4. Okay, any questions on how we did this?
So we only do this, oh, go ahead.
Sorry, you can go ahead.
So we only do this sort of cross canceling on just the first row.
Well, that's a good question. So it turns out that we can use any row or any column. That's what I'm going to state next. All right.
Okay.
And what you can do is if you have more zeros along any row or any column, pick that row or that column, because then the computation is going to be easier. Okay. So that's the theorem actually, that it doesn't depend on what row or what column you actually pick to do the expansion. Okay. All right. Now, okay, so let's do one more example. Okay. So let's do the 2 by 2 case. So this is the example. And let's do the 2 by 2 case just to make sure we get the right situation again. So if I take the determinant of A, which is the absolute value of, we take A, B, C, D here. Okay. So now I'm going to expand along the first row. So that's going to be A. Well, then I take out the first row in the first column and I get D, right? Negative B, and I take out this column and that row and I get C. Okay, so this definition agrees with the old definition. Okay, questions? All right, now what I'd like to do next is I'd like to actually write this in a more compact notation involving what are called cofactors. So I'm going to use a slightly more compact notation. Okay, so definition. So what I want to do is I want to kind of put the minus signs inside of the definition. So let Cij be equal to -1 to the I plus j determinant of Aij. Okay. Now, when we write this, we don't have to worry about putting in the negative ones, right? So this is going to be equal to A1 C11 plus A12 C12 plus A1n C1n. These are called the cofactors. So you kind of put the signs in with the determinant, and then you can write out the determinant in a little bit cleaner form. Okay, so here's the theorem. So the theorem says that one can compute determinant of A by expanding along any row or column. Okay, so let me say exactly what I mean by that. So if I take determinant of A, then I could write this as AI1. So I'm expanding along the ith row here. CI1 plus AI2, CI2 plus AIN, CIN. Okay, so notice that, up here, I expanded along the first row. I can expand along any row now and still get the same answer. Okay. Now, what I can do is I can also expand along any column. So if I fix the jth column, I just expand along that column. So that's A1J, C1J, plus A2J, C2J, plus ANJ, CNJ. Okay, so this here is the row expansion. And this here is the column expansion. Okay. All right, so let's compute this out. I'll show you how you can do something even more elaborate. Looks scary at first, but it's not that bad. So I want to compute the determinant of now a 4x4 matrix. Okay. Now, one thing to think about is that, what are we really doing? If I take a 4x4 matrix and then I expand things out, I then look at determinants of 3x3 matrices, right? And then I use the definition again, and then I can reduce it down to 2x2 matrices. So this is definitely a recursive process. So you just go down in dimension at every step, and then you sort of compute, and then until you get to the very end where you're computing 2x2 matrices. Okay, so you can actually compute the determinant and by just kind of sort of making the size of the matrices smaller and smaller and smaller and smaller. Okay, now in order to compute this determinant, what do you think we should do?
Use the second row.
Oh, good. So let's use the second row because there are lots of zeros. So we're going to expand along this row over here. Okay. So let's do that. Okay. So what's this going to be equal to? It's going to be 0. Okay, so I'm going to put the signs in just to make sure. So this entry is going to be what? It's the 2-1 entry, so the sign is negative, right? Because 2 plus 1 is 3 and it's odd. right? So then I'm going to look at, I'll just write it out. Okay, so I mean, later on, you're not going to write this out, but let me just write it out. So I'm going to take out the first column and the second row. Okay, so that, yeah, I get that. I get -6, -7, 5, and I get 0, 4, 4, right? And then I get 0, and just for the heck of it, let's just write out what the cofactor is. So I'm going to take out the second row and the second column. So I get what, 1, 5, 2, 2 minus 7, 5, and 5, 4, 4. Okay, everybody good with that so far? Plus 3. Okay, so now it really matters. What is the sign, plus or minus here?
Minus.
Minus, okay. So we better keep track of that. Let me just put a minus sign here. Okay. All right. So let's figure out what the cofactor is in that case. So I'm going to take out this, and I'm going to take out that, right? So what do I get? I get 0, 0, 0. Is that right? 3. Yeah, I guess I am going to get 0, 0, 0. Oh, no, I'm sorry. I took out the wrong one. I'm going to take out that instead. Sorry. Okay, so I get 1 minus 2, 2. Okay. And I get 2 minus 6, 5. It's not that easy, right? And then 5, 0, 4. Okay. And finally, I get 0. I get 0 times something else, and that's not going to matter. Okay. So everything with zeros here, we don't care about because the answer is just going to be 0. So I get minus 3 times 1 minus 2, 2, and 2 minus 6, 5, and 5, 0, 4. Okay, now how should we compute this determinant? What row or column should we expand? We could do any one we want, but is there a good one to do?
The third row?
Okay, let's do the third row. Okay, so we get minus 3. So expansion along the third row. So the entry is 3, 1. So 3 plus 1 is 4. So the sign is positive, right? So I get 5 times what? Minus 2, 2, minus 6, 5. Okay. And then 0 doesn't contribute anything. 4 is in what spot? The 3, 3 spot. So 3 plus 3 is 6, so it's even. So again, it's positive. Is everyone following my logic? Yeah.
Yes.
And what's the cofactor here? What's the matrix do I have to take now?
1, -2, 2, -6.
Good. 1 minus 2, 2 minus 6. Very good. And now we're in great shape because we have 5, and then I just have to take the determinant of 2 by 2 matrices, which we know how to do. So the 2 by 2 matrix is minus 10, minus 12. Okay, so it's minus 10 plus 12, which is 2, plus 4. And then the determinant of this is 6 minus a minus 4. Okay, so it's 6 plus 4. So that's going to be 10.
-6 plus 4?
Yeah. Sorry about that. I apologize. You're right. A little bit too fast. Okay. -6 plus 4 minus 2. Okay? It's getting late, so. Is that all right? Yeah. Okay. All right, so now let's finish it off. So minus 3, 10 minus 8 is 2. And so the answer is -6. Okay, did everyone understand how we did this? How we sort of took this determinant of a 4x4 matrix. We sort of strategically looked at which rows or which columns had more zeros than other columns or rows. And we picked the one with the most zeros because then we don't have to compute as many determinants. And then, so the first time we picked the second row, and then we reduced it down to a 3x3 situation. And then we looked at this matrix over here. And we saw that, well, the third row actually had more zeros than any other row. So we expanded along that one. And then we reduced it down to 2x2 matrices, and then we got the answer. Okay, any questions on this?
Yes.
Okay.
So will we get -6 for any row we
Yes.
choose,
Yes.
any call, and then like once we get a 3x3, any row or column we choose there,
Yeah,
and we still get -6.
that's right. That's right.
Wow.
Yeah, it's really kind of an amazing property with the determinant function. Okay, so let me sort of end in terms of, so what I'll do is I will look at an upper triangular matrix. So here's the theorem. So let A be an upper triangular or lower triangular matrix. Okay, so so then if I look at the determinant, it's just the product of the entries along the diagonal. Okay, and so this is not very hard to see. So if you take, let me just do a little justification on this. So let's say A looks something like A11, A12, A1N, ANN, okay? And then there's some entries maybe above this, and there's zeros down here, right? So then, you know, if you do the determinant of A, and all I have to do is expand along the first column, so that's A11, and the determinant of A12, ANN, with some entries up here, right? Because all the other determinants are going to be 0, and then you just repeat the process. This is a 2-2, by the way. Let me rewrite this. I don't want to get too sloppy about this. So let me rewrite this just to make sure it's clear. Okay. So this is an A22, ANN, and this is an A22, so forth and so on. Okay, so then what you do is you sort of repeat the process. So it's A11, A22, and the matrix is A33, ANN, star, and then you just keep going, and then finally you get A11, A22, up to ANN. Okay, so if you have anything which is lower triangular or upper triangular, the determinant is just the product of the entries along the diagonal. So those are really nice matrices to have. Questions?
I just have a comment on this. So when we have some sort of diagonal with a lower triangular, upper triangular, in earlier classes, we could have actually broken those down into like elementary matrices,
Right.
correct? And those always had an inverse.
Yes.
So is that kind of the connection between the determinants and the, like how you can decompose matrices and just find the inverses of them?
Okay, this is a really good question. We're going to answer this next time. So let me just write out what we'll do next time. So next time, we're going to connect the Gaussian elimination process to determinants. Okay, so it turns out that row reduction doesn't really change the determinant. Now, multiplying a row by a certain number without adding it to second row, another row or something, does change the determinant. So we kind of have to keep track of when we multiply a row by a non-zero scalar, and then we have to keep track of how many row exchanges we do. A row exchange will actually put -1 times the determinant. So eventually we'll actually, if you start with A and then you go down and use Gaussian elimination, then the formula will be the product of the entries along the diagonal times -1 to the number of row exchanges. Okay, and we'll justify that next time.
Okay, yeah, that makes sense.
So the answer is yes, there is a definite connection. Okay. And then also I have a formula for a 3x3 determinant. So that we'll do this, and then I'll show you a formula, a quick way to prove 3x3 determinant. Okay, but it doesn't generalize to 4x4 determinants. So only for 2x2 and 3x3, this actually works. Kind of an interesting formula. Okay, and then we'll sort of continue on with properties as determinants, and we'll see how far we get on Friday. I'm trying to push ahead a little bit because right before fall break, well, the week before fall break, we have a short week, and the next week is going to be the midterm week. And so I'd like to be able to get some review in before the midterm. So I'm going to push ahead a little bit and try to create some space for review before the midterm. Okay, other questions?
I'm looking back here, and so does row switching all change the determinant?
Yes. So if you permute two rows, then it's -1 times the determinant. So if I take a matrix and then we have the determinant of this matrix, I have another matrix where two of the rows are interchanged, then the determinant of this one is -1 times the determinant of that one.
Okay, so whenever you have either a scalar of a row or
Yeah.
a permutation matrix,
Right.
when you decompose a larger matrix, those affect the determinant.
That's correct.
Okay, thank
But
you.
generally speaking, we're not going to multiply necessarily row by scalar. So the only thing that's really going to matter are row exchanges in the Gaussian elimination process.
Okay, yep.
Okay, but we'll go over that very carefully next time, just to make sure that we understand exactly what's going on. So, all right, questions? Okay, so again, thank you for joining us tonight, and hopefully on Wednesday things will be somewhat back to normal. Okay, but I'll keep you abreast of the situation. Okay,
Thank you.
have a good night.
Thank you.
Thanks.